Right, thank you. So I'm going to talk about high-resolu quasars and how to use them to probe the evolution of supermassive black holes and the intergalactic medium of the epoch of ionization. So the first quasar was discovered like almost 60 years ago now. And since then, of course, quasars have always been one of our primary tools to study the distant universe. This figure has been used in the last maybe 15 years or so of sort of highlighting what we knew about the most distant quasars. There was a summary of all the quasars that was known at redshift about 6 in a review paper 2006. At that time, most of these quasars are discovered from the Longitudinal Sky Survey, and there are handfuls of them. But even at that time, there were sort of 3 main conclusions about what's going on in those quasars and how to use them to probe distant universe. One is, of course, the existence of these objects. These are luminous quasar redshift beyond 6, tells you that the supermassive black holes powered by sort of billion solar massive black hole already existed about 1 billion years after Big Bang, so you have to form them really quickly. The second point is these quasars have their host galaxy that have a lot of hot dust emission in it, tells you there's these objects are accompanied by intense star formation in their host galaxy. And the third point you can see here is on the blue side of the landmark emission line here. Of course, that's the strong Peterson absorption, indicating that at that epoch, the universe is getting more and more neutral. There are a lot more neutral hydrogen line of sight in the IGM. So we're seeing the ionizations ending. So that's all of the state of art of 15 years ago. Since then, there are a few more quasars discovered. There's actually now about 1,000 quasars that we know are redshift higher than 5, about 200 are redshift higher than 6, and 10 are redshift higher than 7. So it's very hard to plot all the quasars in a diagram look like that now. So we actually produce this 2-dimensional plot. So basically, these are like 500 something quasar spectra. One line is a 1-dimensional quasar spectrum, just older than my redshift. So what you see here is really the Lemma emission line marched through the wavelengths from sort of redshift 5.5 also at 7,000, 8,000 electrons, all the way to beyond 1 micron at higher redshift at 7.5, 7.6. So the Lemma line finally, instead of UV line, is really now a infrared line now. And what you can see, in addition to this strong Lemma emission, of course, the signature of these quasars, is again the very strong absorption on the blue side. Here, there's basically no flux left when you go to redshift beyond 6. And when you go to redshift lower than 6, you can see a little bit of flux that indicating, again, the ionization is progressing this way as the universe becomes more and more neutral. So that's the sample we have now. And what that enables us to do is to probe to the highest redshift beyond 7, and also have very large sample of objects at those redshift sort of 6 range to probe the end of ionization. And what enables to do that is really a combination sort of 4 factors. One is the new generation of wide area optical and infrared sky surveys. So starting from the SDSS time, 10 stars, dark energy survey, the DESI legacy imaging survey, and various near infrared surveys allow us to detect these objects. These are surveys that cover, and of course also the Subaru HSC survey. These surveys cover basically the majority of the actual galactic sky already to reasonable depths. And then you have to find these objects, select these objects from the photometric database. You're going to hear, I think, the next 2 talks about some more detail about how people actually do that, to do this kind of real object selection and fighting against all the contaminants. But even that is not quite enough. Next step, you have to do effective, sort of a very efficient spectroscopic identification, and that's where Gemini begin to come in. Have to use sort of 8 to 10 meter telescope to take a spectrum to see whether it's a quasar or not, and what the rest of this. And finally, multi-wave waveform solar observation to probe the property of these objects. The last 2 steps are the steps that Gemini has played a fairly significant role in our study. Let me just show you sort of 3 of our post-child most distant quasars. This object was discovered 3-4 years ago now. It was the most distant lensed quasar, and also the brightest quasar we know, the bright object really we know in the distant universe. This is a redshift 6.5 quasar at 18 magnitude. So I mean, you all heard about the news about all the LRFC stuff. A similar redshift, we're talking about 28 magnitude. This one is 18 magnitude, redshift 6.5. Literally at the end of in the middle of renovation. The reason is this object is actually strongly lensed, magnified that factor about 50. So that's the most distant lensed object. If you have time, we'll come back to talk a little about how the lensing is going to help us to understand the black hole growth. But the spectrum, the discovery spectrum, actually a combination of MMT, CAT, and GNERS particular here that provides the infrared coverage of this object, and in particular allow you to go to sort of a K-band to use the magnitude emission line to actually to measure the black hole mass. You sort of assuming the line was caused by gravitational motion. The second object was discovered a couple of years later. This is a redshift 7.52 quasar, which at that time was the second highest redshift quasar. It was discovered at Gemini North using GNERS. And you can see the spectrum here. Again, the GNERS really get you to the very far end of K-band, allow you to measure the black hole mass. And this is actually the first object with a billion solar mass black hole that we know at redshift beyond 7. So we're pushing sort of towards the most massive black hole at the most distant at the highest redshift. And we're very glad and sort of fortunate that the observatory was able to work with the Science Center in Hilo and give this object a very good name, Hawaiian name, Ponoua Ena, which means unseen spinning source of creation surrounded with brilliance. I believe this is the first quasar that ever was given an 18 Hawaiian name. So we're really sort of fortunate to be associated with this effort. So that's the second discovery. The third one is actually the most distant quasar that we know today. It was actually we discovered at the very last observing run we were able to do in person before everything. So it's a redshift 7.64 quasar. But you can see actually it just shows you that in order to get the final spectrum, the relatively faint object, we actually used a whole bunch of 8 to 10 meter, 6 to 10 meter telescope to get this combination to really get all the way from below Landmark emission to again the end of K-band. And that's really where GNERS actually shines, because there are few crowd dispersing spectra that cover sort of intermediate resolution and infrared. There's fire on Magellan. There's nearest on CAT, of course, X-shooter, and GNERS. What GNERS is really good at is the far end of the K-band that nobody else actually can reach to. And that gives us really this line to get a black hole mass. And the other interesting about this particular quasar, not only the most distant one, but you can see the absorption feature over here. And that is actually absorption for the absorption line feature coming from sort of highly ionized lines tells you there's actually a very high velocity, sort of beyond 0.1 C. These are outflows coming from the sort of central part of the AGN, tells you whatever the quasar is doing is producing some kind of feedback in the galaxy at those points already. And this kind of quasar is really becoming more common at high redshift. So that's a discovery. And let me, so another question is, so now we know we reached to redshift 7.5 now. So how far more can you go? We heard about redshift 20 galaxy yesterday. I don't think we're going to get redshift 20 quasar very easily. The reason is the quasar density is dropping really fast when you go to high redshift. The redshift 7 quasar we're talking about is about 1 per cubic gigaparsecs. These are the sort of rarest objects in the early universe. And if you're just extrapolating this density evolution and sort of ask the question for this kind of luminous quasars, at which point you get only 1 in the entire observable universe, basically in the entire 4 pi. You get this point by redshift about 9. In other words, if you're talking about sort of so-called SDSS kind of quasars, these are objects again powered by sort of hundreds million to billion solar mass black holes. We're running out of universe, really, volume of the universe at redshift about 9 to 10 or so. And the way to do that, to find these objects, is really the next generation sky surveys, Euclid and Roman, infrared plus Robin analysis T in optical. And the challenge there is when you can detect them, how to identify them again. So there is really a combination of, again, things like Gemini large ground-based telescopes for this kind of initial identification we're talking about, except you have to go to even fainter magnitude. and then using JWST for detailed spectroscopy to actually understand their properties. All right, so now I'm going to just very quickly go over some highlights of what we learned about these quasars in terms of their connection to early galaxy formation. Is actually we can see the connection of quasars with galaxies in sort of 3 different scales. At the scale of event horizon, at least scale within the sphere influence of the black hole, we can look at the black hole mass and their properties to see how black holes are seeded and grow. At much larger scale, the galaxy scale, we can see the host galaxies and how quasars impact the growth of the really massive galaxies. And an even larger scale, 100 megaparsec scale, quasars, of course, are used to probe ionization that we talked already. So in terms of black hole growth, these are a compilation of all the black hole masses that we have on those quasars. Again, the way that we measure black hole mass is to go for these broad emission lines that are coming from fairly close to the central black hole, so well within the spheral influence of the black hole, and use the width of the line as sort of like a proxy of how fast gas is moving. We're going to hear more on Friday of how to measure black holes mass in local universe, but this is about as good as we can do. And these black hole masses, you can see, are sort of a ratio of 7 also up to billion solar masses. There actually is one object that we have still trying to understand what's going on, maybe up to about 10 billion solar masses. Again, a ratio of 7. So this is within a few hundred million years from the first star formation in the universe. How can they grow that fast without a problem, right? So if you're assuming these black holes are here, there's redshift, there's mass, and assuming they are creating as fast as they can, Eddington rate, as often as they can, 100% duty cycle. And then the quasar, the black hole mass sort of double every 30, 40 million years. And then extrapolate to see what kind of seed you need at whatever the redshift is. You can see that even if you form these black hole seeds at redshift, say 30, and ask them to just continue to grow nonstop, you still need 10 to the 3 to 10 to the 4 solar mass seeds. So that is beyond what you can do with things like the collapse of, say, population 3 stars. You have to have more exotic way of forming these very massive systems, such as so-called direct collapse black holes. How do we go there? I think that is really the question that the next generation of study have to address, is because now we're just posing the question. We find the end product of this black hole growth process and really need to go to earlier stage that are fainter, more obscured, to figure out exactly how the black holes form and grow in their initial phase. But so the second point is about the black hole galaxy connection. Their optical infrared observations is going to be very hard because you have this bright quasar in the middle. So the way we do it, of course, is to go to longer wavelengths. There's what ALMA is playing a central role. ALMA both can sort of detect the dust emission coming from the star formation in the host galaxy and atomic and molecular gas in those host galaxies very, very quickly. So you can do sort of 10, 15 minutes snapshot and detect both of these quasars already with ALMA. And then you can turn around and really looking at what's going on with this object. There's a couple of examples of extremely high spatial resolution observations. You can see the sort of sub-kiloparsec scale observations of the host galaxy of these quasars. And to highlight these two objects, because they're showing a lot of contrast of the kind of galaxy they're living in. One is huge, with the velocity field sort of look pretty massive, with even some holes in the middle. Who knows what's going on with some feedback or what? The other have the similar black hole mass, exactly same redshift, much more compact, have a nice velocity sort of gradient that's suggestive of this object is actually rotationally supported. That's the thing that we're seeing. Sort of when you see these quasars are similar properties, similar luminosity, similar black hole mass. But when you look at the galaxy properties, they actually look very different. Some of them are rotationally supported. Some of them look like some kind of dispersion dominant system. Some of them look disturbed with some merger or companion activity in it. But overall, these are strong star formers, highly turbulent systems with a high gas mass fraction, very high molecular gas mass. The other thing we can do is when we have this high spatial resolution observations, we can actually measure sort of or estimate the dynamical mass of the host galaxy and compare that with the black hole mass. So again, that's the sort of M sigma relation that we we're familiar with, we can plot these quasars at redshift 6 or 7 onto the local velocity version with black hole mass relation. What you see here is, at least for the object that we're talking about, they're about factor of 10 above the local M sigma. In other words, these objects are forming black holes faster or earlier than the assembly of the galaxies. Now, one of the really exciting things is whether we can really probe exactly what the black hole is doing to the galaxies. And that comes back to this lensed quasar I mentioned earlier. Because this object is so bright, it's actually probably the brightest object in the early universe in almost all the wavelengths because of the lensing. This is ALMA observation that actually show the sort of nice arc from the lens. But the combination of how bright it is and how high the magnification is means you can really go to high resolution. This is the resolution about a quarter of a second. We actually have a higher resolution observation from ALMA that really shows this nice feature over here. And the highest magnified part of this image have an effective resolution of about 20 parsec. So we're talking about 20 parsec resolution observation with this ALMA observation at redshift 6.5. That actually gives us really close to black hole. We're hoping to figure out what exactly that thing is doing there and whether we can constrain the animal mass. Okay, so finally, very quickly about reionization. It all started with sort of detection of complete Compton absorption at redshift higher than 6. But now we have all these quasar sight lines. What you see here is this is a transmitted flux, or how transparent IgM is, a function of redshift of all the quasars we have. What you see is, again, sort of a progression from transparent to opaque, so from the universe higher ionized to become equilibrium neutral. But the other thing we learned is that this process of ionization, how fast the universe is going from ionized to neutral and neutral to ionized, is highly sort of fluctuating in the sense that there are a lot of line of sight dispersion over redshift 6.5, 5.5 to 6. Some of the sight lines are very, very dark already at those points. Other sight lines are still transparent. So if you put everything together for the reionization picture, you see this is all the constraint coming from quasar observations. You see the initial rise over here, redshift 6.5 to 7, 5.5 to 6. That we think the end is. We think the peak of reionization is really at redshift 7.5 or so. That's where the universe is probably half neutral. And then there's actually still a pretty big gap in the middle that we think our new quasar sample is going to fill in to map out exactly how you go from 10⁻⁴ neutral fraction in the IGN to about half over the period of only a couple of 100 million years. All right, so I'm going to end with what's going to come next. We're all waiting for the velocity data. So there's actually a very large high-resolution galaxy quasar program in cycle 2 from both GO and GTO, cover about sort of 40, 50 quasars over in the redshift 6 to 7.5 range, over a very wide luminosity range. And our hope, these are simulated data. Hopefully in the next 2 months, we're going to change that to real data. The hope is really to use the JWST to detect stellar light, to measure stellar mass with an increasing sensitivity, and then to connect them to quasars, to galaxies with larger structure, and also to probe IGM galaxy connection with all different sight lines. And yesterday, I think people are talking about what role the ground-based large telescope play in the JWST era. At least for quasars, I think there are 3 things where we think the ground-based observation is still going to be crucial. One is, again, you need the 8 to 10 or later on GMT and TMAN to find them, because JWST is going to be slow to follow them up, or it's not efficient to do it. So they are still the discovery machine. Of course, we still have the optical wavelengths all the way up to 1 micron or so. That's where we're going to end up probing more detailed end-hour ionization. And finally, JWST, of course, have very sensitive spectroscopy, but it's not going to go to R of 30,000 that we really need to probe IgM enrichment, to measure IgM temperature, and so on, to map the entire picture of ionization. So the high sensitivity, high resolution infrared spectroscopy is still needed. But finally, I'm just going to put a summary here. I want you to sort of take back these three pictures that I think highlight what we know about the highest redshift quasars. They form early, and I think we're actually getting very close to time where we can ask the question when the first luminous quasar appeared in the universe. They live in diverse galactic environment. I think JWST is really going to tell us, in a combination with ALMA, tell us what kind of galaxies they are in. And ionization as told by quasars seem to be rapid and inhomogeneous. And this redshift range is still the range that of ground-based optical observations is going to be very important. It's actually going to be redshift 6 or 7.5 is going to be the astrophysically most interesting range of redshift that more progress will be made. All right, thank you.
Thank you. Is there any questions from the audience here or Slack?
No questions on Slack.
No questions? Oh.
That was a great talk. Thanks very much. I'm sure you've noticed in the last week a whole flurry of papers of redshift, all the way up to 14, 15 galaxies. I don't know if any of those show any kind of AGN signatures, but have you thought about, what those first quasars might look like? And then also I'm curious what the duty cycle is, right? Because some of these first galaxies, we're detecting them, they're relatively bright the first pass here. And are they massive enough to be hosting quasars? And
right,
how frequently would you observe it?
I mean, I'm sure there will be a lot of work on the AGN aspect of these galaxies. The thing that we learned from, at least from HSD of the one slide I couldn't show, is actually they are among the one of the interesting recent work is actually there was a detection of a radial and strong sort of MIPS infrared detection of one of the most massive lemon break galaxy in the cosmos field. So there's clearly AGN activity in it. And actually that object is, we still don't know what's going on. That object is so massive in terms of, or so luminous in terms of the AGN power of volumetric luminosity, that it somehow doesn't make sense of how rare, how in 1 degree you can find it. So I think there are a lot of things we don't know about galaxies and about AGN in very high galaxies that JWST will play a huge role in it. Probably the best way to probe that is actually, one is you can go to mid-infrared, but that's probably still fairly faint. The other way is a variability, right? So I'm hoping that there will be multi-epoch observation to really figure out how many of these things are changing, because if the black holes are small, you will see them changing in a few months time scale or year time scale.
Okay, and if I could ask a second question, you highlighted the power of G-nears in identifying spectroscopic features way out into the K band. And of course, we're really excited to have these new IFUs coming on. Do you think that the IFU capabilities, particularly with the AO, would be useful to probe at the host galaxies?
I think they will certainly be useful for probe sort of slightly larger scale than the host galaxy. I mean, one example is actually we have a program on using Muse, sort of go to redshift 6, slightly lower redshift than. Then what you will see here is with Muse, with sort of their semi-AO mode, you see quite a bit of, or even without AO, you see quite a bit of lemma alpha halo around these quasars. So probably not the host galaxy itself, because that's hard, because the quasar is too bright. But when you go to a few, because and the host galaxy is supposed to be fairly compact. So I think going to 1-2 kiloparsec is difficult. Going to 5 to 10 kiloparsec is really good. Because what we see from Muse is that when you go to that scale, there are a lot of lemma alpha halos around it. You can actually even see the rotation of these halos. That tells you something, sort of giving some dynamical information about the gas going on there. So I think that is really sort of on the scale, on the edge of the galaxy, or right between galaxy and CGM is one that I think the sweet spot is.
Thank you.
Thank you very much. Is there any questions? Then thanks.
There's no one question. Like,
yeah, did you have a question? I saw your hand was up on Zoom.
Yes, I didn't know if I should ask on Zoom or if I should post the question on Slack, but
yes, please go ahead.
I was wondering about the M sigma relation because you showed that there are black holes that were very massive and above the relationship. But I've seen some recent models that show something the other way around, that star formation could prevent the black hole from forming because of feedback. Is that maybe because of a bias that we cannot observe the low mass black holes at these redshifts?
Yeah, I think that's exactly right. I mean, the objects that we see are the most extreme objects. The reason that we see them is because there is a black hole in it. But the occupation fraction, for example, of these objects that Jen just mentioned is going to probably be low. So some of them we were seeing the extreme example of a big black hole in a galaxy. There must be the other way around. Some of the galaxies didn't blow a black hole very efficiently. I think that's exactly right.
Okay, thank you.
Right.
Let's thank speaker again.